Hello everyone and welcome to Everything's Relative with me, Mr. K, where today we're going to be turning our attention to AS Physics for Cambridge 9702 and specifically Paper 1, Variant 1 from the May-June exam series 2022. So if you're watching this more currently, this is the exam from a year ago. And as we know, Paper 1 covers only AS content and not the full A-level content, but it is multiple choice. So some people love it, some people hate it, but multiple choice can be tricky. So we aren't going to cover the content in detail in this video, but I will go over how to answer the questions in this paper. And remember, you have just over an hour to answer this paper and there's 40 questions. So there isn't much time to do a lot of thinking and problem solving. So a lot of the concepts have to be understood well before you walk into this exam. And so when we start this paper, we always start with the topics of physical quantities, significant figures, and units. And we can see this in question 1. Question 1 says, which term represents a physical quantity? Okay, so I'm given 4 terms, A, B, C, and D, and I have to read all of them to get my answer. Meter is option A, percentage uncertainty B, C, quark flavor, and D, spring constant. Now I have to remember and recall immediately what a physical quantity is. And a physical quantity is anything that's measurable, it's observable, and most importantly, it can be represented by a magnitude and a unit. And so immediately we can see that we can eliminate meter, which is just a unit. We can eliminate the concepts of percentage uncertainty and quark flavor, but spring constant is something that we can measure with both a magnitude and a unit. So the spring constant K is indeed a physical quantity. We can measure it with a magnitude and we can measure it in newtons per meter. So it has a unit as well. And so the correct answer there would be D. Always just make sure you're going back to your textbook, going back to your notes to understand what these terms mean. You still need to understand definitions if you're going to go through paper 1. Question 2 says, which 2 units are identical when expressed in terms of SI base units? Now, I can see on the left-hand side, I have derived units. I have joules and newtons, etc. And on the right-hand side, I have base units, kgs, meters, amperes, seconds, and so on. So I could go and do this option by option, which will take a long time, but will obviously ensure I get the right answer. But what I also can do is wherever I'm doing my working, I can be a bit clever about this. I can say, well, let me take a newton and a joule, which are the derived units being expressed on the left-hand side, and convert them to base units. And I'll write it down explicitly. So a newton is equivalent to a kilogram meter per square second. How do I know this? Well, from the mathematical form of Newton's second law, F is equal to ma. F is measured in newtons, resultant force is measured in newtons, mass in kg, acceleration in meter per square second. And so that's how we get the unit for the base unit that's equivalent to a newton. What about a joule? So a joule is equivalent to a kg meter squared per second squared. So it's basically the unit for force multiplied by another meter. How do I get this? Simple. I just recall that work done is equal to the force applied in an object multiplied by the distance in the direction of the force. I don't have to worry about the cosine theta since that's dimensionless. And so work is force times the distance. And so I take the unit for the force and multiply that by another meter. So I get kg meter squared per square second. So what I can see almost immediately is that a joule second, and again, these things, you either do it by calculation, step by step, or sometimes you just by observation, by looking for a pattern or seeing something that stands out to you, you can reduce the amount of time it takes to do these questions. A joule second is a kg meter squared per second squared, and then multiply by a second. And so this unit is a kg meter squared per second. And this is indeed is one of the options. And so this has to be the correct option. And that correct option is B. And there can only be one correct answer. So if you're confident that your mathematics is correct, then you know that your answer is B, and it saves you time from having to check each of the others. So it's a combination of doing the relevant mathematics, but also being able to have the eye to see when something stands out. So paper 3 is indeed not as straightforward as we usually think it is. Question 3 tells us that a value for the acceleration of free fall on Earth is given as 10 plus or minus 2 meters per square second. Now we know that indeed g is 9.81. So some experiment gives us a value of 10 with an uncertainty of plus or minus 2. So what this means is our uncertainty, or absolute uncertainty, delta g, is 2 meters per square second. Now, let me write this. It's not necessary, but let me write this as an uncertainty. So the four statements here say the value is accurate but not precise. B says the value is precise and accurate. C says the value is neither precise nor accurate. And D says the value is precise but not accurate. So the two important words there are accuracy and precision. And so to test the accuracy or the precision of an answer, I'm going to, again, I don't need to do this, I can just tell, but if I find the percentage uncertainty in this value, delta g over g times 100, I get this to be 2 over 10 times 100, which is a percentage uncertainty of 20%. So what I can see is the value of 10 is okay. It's fairly close to 9.81, so the accuracy is there. But what I can see is that it varies quite a large distance away from 10. It goes 2 less. It ranges from 8 all the way up until 12. And so although it's accurate, although the central value is fairly close to the accepted value, the measurements are too scattered. And so the measurement is accurate but not precise. And so accurate but not precise is option A. And again, just make sure you read up on accuracy, the difference between accuracy and precision, and ensure you understand what that means. Moving on to question 4, we are told that 2 cables are attached to a bracket and exert forces as shown. So we're moving swiftly on to a little bit of dynamics here with forces. We have a bracket, a 15 Newton force at an angle of 20 degrees to the horizontal, a second force of 6 newtons at an angle of 40 degrees to the vertical. What are the magnitudes of the horizontal and vertical components of the resultant of the 2 forces? Okay, so I need to do a little bit of vector analysis here. So I think the best thing for me to do is probably to draw a force diagram. And so what I'm first going to do is I need to find the horizontal component and the vertical component of the resultant of the 15 Newton force and the 6 Newton force. So what I will do is draw them head to tail. So I'm going to draw the 15 Newton force in that direction, and then maybe with a different color, draw the 6 Newton force. Now I'm not drawing it to scale because I'm not going to be using a ruler to try and to find the resultant. I'm going to do it mathematically. And then maybe I use the same color for both the given forces and a different color for the resultant. And so if I were to draw it to scale, I'd find that my resultant force points to the right and slightly downward. And I need to find the y and x component of the resultant force. So what I need is that y component and that x component. I'm going to call this unknown force, this resultant force, F for simplicity. This will be Fx, and that will be Fy. Now we can also break our two given forces into their components, y and an x, and for the second force, similarly an x component, which is to the right, and then a y component, which is downward. So what I have is that this is 15 newtons, that is 6 newtons, and then with a little bit of geometry, I have an angle here that's 40 degrees to the vertical. And if I draw a horizontal for the first force, the 15 Newton force, the angle is 20 degrees. So a lot of mathematics going on here. So what I'm going to do is first find Fx. Now Fx is the x component of the resultant force. And guess what? It's going to be the sum of the x component of our two given forces. And so with a little bit of geometry, for the 15 Newton force, its x component, which is the horizontal black line, the long black line at the top, is its magnitude, 15 newtons, times the cosine of the angle that the force makes with the horizontal, which is 20 degrees. But the resultant force also has a part of its x component provided by the second, smaller 6 Newton force, since it's also pointing to the right slightly. So I have to add that x component. What is confusing is now the angle is with the vertical rather than the horizontal. And so it's that magnitude, which is 6, times the sine of 40 degrees. Again, it's just a little bit of geometry, not anything too complicated. So that gives me the x component of the resultant force. And if I evaluate this, I get 18 newtons. Now, if I do the same for the y components, then all I do is replace sines and cosines. For the first 15 Newton force, I'm omitting the significant figures as I shouldn't do, but you will obviously include them when doing the calculation. So for the y component of the 15 Newton force, that's 15 sine 20 degrees, plus the y component for the 6 Newton force. Now it points in the opposite direction, since if we choose upward to be positive, and to the right, upward is positive y-axis, and to the right is a positive x-axis. Since the 6 Newton force points downward, it's opposing the 15 Newton force. This is going to be a minus. So we replace the plus with a minus 6 cosine 40 degrees. So there's a nice little symmetry here between the two equations. And this gives us 0.534. This is where the significant figures are important. This should be 15.0 and this should be 6.00. And so we preserve our three significant figures. And what do you know? Fx is 18, Fy, which is horizontal, that's the horizontal component, and this is the vertical component. And guess what? This corresponds to option C, 18 and 0.534. And so that corresponds to option C. So a little bit of mathematics. This probably would require some actual physical written work and a little bit of mathematics. You could do this using a ruler, and you could do this using a scale diagram. I do feel, however, it's just safer to use the mathematics to solve a problem like this. Okay, question 5. So question 5 gives us a curved line, PQR, which is the velocity time graph for a car that is starting from rest. And they ask us what is the average acceleration of the car over the first 5 seconds. The area below the curve PQ the area of the triangle PQS, the gradient of the straight line PQ, and the gradient of a tangent at Q, specifically at the point Q. I think the first thing to do in a question like this is to remind ourselves what average acceleration is. Average acceleration, or acceleration in general rather, is rate of change of velocity. And so if we have a velocity time graph, the rate of change of velocity will be the gradient of the graph. And so it's the gradient, but where is it the gradient of the straight line PQ or the gradient of the tangent at Q? Now, the average acceleration, remember, we have a velocity time graph that's curving. And what that means is the acceleration is not constant. Car starts from rest and the acceleration increases, which results in a curved velocity time graph. Now, average acceleration will be average gradient. And so what is the average gradient? It is the gradient of PQ. So it's the gradient of the straight line PQ. I mean, it's impossible to find the gradient of a curved line over a region, but you can find the average gradient by drawing a straight line from P to Q and finding the gradient of that. And so that corresponds with option C. And so that's the gradient of the straight line from P to Q. And so that's for the first 5 seconds, and that's why we choose PQ specifically. And so the average acceleration will be a certain value, but that's not the acceleration at any given point in time. It's the acceleration that's an average value of all the accelerations over that period of 5 seconds. So we have to understand what velocity is and how acceleration relates to velocity, and also we have to understand the graphs. Hugely important to understand how the graphs relate to those quantities and how we can use the graphs to determine some of those quantities. Now, question 6 says that a ball is thrown horizontally with a speed of 10 meters per second above horizontal ground. The ball hits the ground after a time of 3 seconds. If air resistance is negligible, what is the speed of the ball just before it hits the ground? So again, this is more than likely going to require some calculation. So again, not necessary, but I'm going to draw a diagram. Here goes the ball with an initial speed that's horizontal, u, of 10 meters per second. It's above horizontal ground, and so it will follow the parabolic path. When it strikes the ground, it has a final velocity v, and this velocity v, we're assuming it's moving to the right. It doesn't really matter. We can choose the right to be positive, and we assume that it moves to the right. And this final velocity v has components vx and vy. And this is just before it strikes the ground. Now we want to know the speed of the ball just before it hits the ground. So what we can do is we can find the vertical component of the speed just before it hits the ground, vy. And it's using a simple equation of motion. V is equal to u plus a times t, where uy is the initial speed in the y direction. But guess what? U is ux. There isn't a y component. The ball is thrown horizontally, so the initial speed in the y direction is 0. Plus the acceleration. Do we have the acceleration? Well, yes, we do. If we choose down to be positive, since we have no upward motion in this entire scenario anyway, the acceleration is only due to gravity. There isn't any other acceleration on this object. And the time it takes to reach the ground is 3 seconds. And so it simplifies nicely, and we get a final y component of velocity of 29.43. I mean, we want the final velocity in totality, so you could just leave the product as is. If you are keeping an answer, make sure you keep many significant figures so that when you do your final calculation, you have greater precision. but I don't have Vx. Well, what I know about projectile motion is that if air resistance is negligible, like it is in the question, then I don't have to worry about the horizontal component of velocity changing. So Vx and Ux are the same, and that's 10 meters per second. What does this mean? This means I can find the final velocity v with some simple algebra. That's the square root of Vx squared plus Vy squared. And that's the square root of 29.43. Again, all my units are in SI, so I can just write them as is, squared plus 10 squared, which gives me a final velocity of 31 meters per second. And this corresponds to option C. And so that is option C. Now, question 7 says an object is moving along the ground in a straight line at a constant speed. Two important points. Which statement about the resultant force acting on the object is correct? So again, I'm going to have to read through these statements to see which is correct, but this shouldn't take me too long. The resultant force acting on the object is equal to its weight. The resultant force acting on the object is equal to the product of its mass and velocity. The resultant force acting on the object is equal to the resistive force, and the resultant force on the object is equal to 0. So what I do know is that the object's moving in a straight line and it's moving at constant speed. And so those two things tell me something very important. If I go to Newton's first law, I know that an object moving, or rather second law, an object moving at a constant speed has no acceleration. If it's not accelerating, the net force on it must be 0, which obviously then brings us to the first law. Any object that does not have a resultant force on it will continue to move at constant speed or stay in its position of rest. If it's moving at constant speed, all the forces on it must be balanced. And so if I were to draw a diagram, I don't need to do this. I have an object with, on a surface, normal reaction force acting upward, the weight of the object acting downward, some applied force we'll call uppercase F acting to the right, and some resistive force acting to the left, we'll call it lowercase f, friction. All these forces must be balanced. And so the net force must equal to 0. And so what we know is the resultant force acting on the object must be equal to 0, and that's a result of Newton's laws. And so this must be option D. So option D must be the correct answer for question 7. It's very important to understand Newton's laws as well, because more than likely you're going to be asked some sort of interpretation of Newton's laws. Okay, so question 8 says, water flows out of a pipe and hits a wall. When the jet of water hits the wall, it has a horizontal velocity v, cross-sectional area a. The density of water is rho, and the water doesn't rebound from the wall. We want to know the force that is exerted on the wall by the water. So this is a very different type of question. It's not something that you have seen before, but it obviously they expect from you that you can derive the equation that gives us the force. So what am I going to do? Well, I'm going to figure out a way of getting the correct equation. And I think the best thing to do, since I don't know fluid mechanics because I haven't studied fluid mechanics, is to do a dimensional analysis to find the units that's going to match with the units of a force. So if I play around with the units, I know the unit of measurement of force is kg meter per square second. So what I can do is I can go and find the units of measurement for each of these options individually, and see which of these match. Or I could look for a pattern by manipulating these units as they are. So what I can do is I'm going to write this as kg per cubic meter times a meter squared times another meter squared times second to the minus 2. Now, if you notice, these two are equivalent. The kg remains the same, the second to the minus 2 remains the same, and m to the minus 3 times m squared is just m. Why did I do it in this way? Because if I look very carefully, a kg per cubic meter is the unit of measurement for density, for mass density, rho. I'm going to use square brackets to denote the units here. And a meter squared is simply the units of measurement of an area. And what I'm left with is meter squared per second squared, which I could write as a meter per second all squared. And that's the unit of measurement of velocity squared. So that's rho times a times v squared, which is indeed one of our options, option D. So even though I don't know fluid mechanics, I can take my understanding of making sure that equations are homogeneous and find the equation or the units that match the units of a force, and hey, I have the units of measurement. So you shouldn't spend time trying to recall what the equation of a jet of water is, because obviously we haven't studied it. If you get a question like this, quickly go to dimensional analysis and try to find the units that match the units that you want. So question 9, we're still on forces and projectile motion. Question 9 says a projectile is launched at an angle above horizontal ground and travels through the air. So we've shown the path of the projectile. The projectile reaches the maximum height at position X. If there's no upthrust acting on the projectile, we want to know which diagram shows the direction of the force or forces acting on the projectile at position X. Okay, so all we are told is that no upthrust is acting on the particle. We are not told that no friction or no air resistance is acting on the projectile. And so if I were to plot its path, so up goes the projectile, then at a position X, it reaches its maximum height. At this point, it has a velocity that's to the right, Vx, and then the particle comes back down. Now, if I consider the position X, and I draw the free body diagram of this particle, or this projectile, then we know that the weight acts downward. So there's definitely a force acting downward. So we can immediately eliminate C. There must be force due to gravity, the weight of the particle acting downward. But I don't see an option that only has the weight. So there must be another force acting on the particle. Since we haven't said anything about neglecting air resistance, there must be a frictional force acting the projectile as well. But remember, resistive forces oppose motion. The motion of the particle is to the right, the resistive force must be to the left. And so we have a force acting to the left and a force acting downward. And there aren't any other forces acting on this projectile, since we are assuming that all fluid forces can be neglected, like upthrust. There are only two forces on the particle, to the left and downward, which corresponds to option B. So you can see these questions are not straightforward. It's not what you remember from reading through your notes. It's application of the concepts. The more problems you do like these, the better it becomes. So studying for paper 2 is very different to studying from paper 1. The types of questions are different. The questioning styles are different. So make sure you prepare well in advance. Question 10 says, what is a statement of the principle of conservation of momentum? Well, you know what? I'm just going to write it down mathematically to remind us. The principle of conservation of momentum says that for a closed system, if no resultant force acts on a system, then the sum of the momentum or momenta of the particles interacting in that system must always remain constant. Okay, and if we're considering them to be vectors, then more specifically, they must always be equal to 0. So the momenta, we consider them as vectors and treat them as vectors. The total momentum of the system must always equal to 0, provided there's no external force acting on the system. But all that I've said by writing this mathematical equation corresponds to option D. And so I don't even have to do any writing. I can simply circle the right answer, provided I understand what momentum means and what the principle of conservation of momentum entails. So you've saved yourself some time in a question like this without having to do any detailed sort of working. So the time that you would spend doing longer questions, you can now at least pull some time back by these shorter questions that just require a bit of reading and an answer. If you're uncertain, my suggestion would be don't take too long. Mark it with an asterisk or a star, or circle the question, come back to it later. Okay, so that's a quarter of the paper done, the first 10 questions down. Now we're moving on to rotational dynamics. We're told that a horizontal wooden plank is pivoted at one end, as shown. The plank has a mass of 100 kgs and a length of 10 meters. The center of gravity of the plank is a distance of 4 meters from the pivot. What is the moment of the weight of the plank about the pivot? Okay, so this question does one thing nicely, which is to tell us what the pivot is. Okay, so this is the type of question where you're going to take a bit longer, but the time that you saved from the previous question now becomes a little bit more invaluable. So for question 11, what I'm going to do is just maybe redraw this diagram poorly, but I am a physics teacher, not an artist. So there's my plank, believe it or not. It's pivoted at the left end. The center of gravity is not at the center. So it's not our usual object, but the good thing is that at least they told us where the center of gravity is. The distance from the pivot to the center of mass is 4 meters, and the total length of the plank is 10 meters. And so if I draw the forces, there's a weight acting downward here through the center of mass. So the weight, remember, of any object always acts through the center of mass of that object. We consider the object to be a point mass, and the weight acts vertically downward from that point. And this is a 100 kilogram plank. Again, you don't need to draw this. You could visualize this. It's not that difficult of a problem. So what I want is the moment. Now, I don't really have a symbol. Well, at least for us, there isn't a symbol for moment, so I'm just going to write moment. The moment of the weight of the plank about the pivot. There's only one force acting on this plank, which is its weight. Remember, moment is the force multiplied by the perpendicular distance from which that force acts to the pivot, or the lever arm as we call it. And so this is a force which is the weight of the plank, which I know is 9.81 multiplied by 981 newtons, sorry. That's 981 newtons since its mass is 100 kg. So that's W is, I confused myself with the mathematics then. 100 times 9.81 is 981. Yes, maths all checked, that's fine. And it's acting at a distance of 4 meters from the pivot. And so it's going to cause the plank to rotate clockwise as we look at it. In this moment, is 4 times 10 to the power 3, or 4,000 Newton meters. And this corresponds to option C. So what did we do? We took the weight of the plank, the only force. We saw that it's going to cause the plank to rotate clockwise, which is irrelevant in this case. And we multiplied the weight by the perpendicular distance of the center of gravity from the pivot point, which is 4 meters. And yes, the weight is 981 newtons. So you could have done this without any drawing, without any significant calculation. So in actual fact, this wasn't really that much of a long question. And so the moment is 4 times 10 to the 3 Newton meters. Always make sure you are checking the units in each of the options, because it's very likely, it's very possible at least, that they could give you an option that says 5 times 10 to the power 3 newtons per meter to maybe throw you off. And so you have to be very careful with the actual selection of your choices. My suggestion would be to choose your options here, pencil, and then if you have, or when you have time at the end of the exam, to then just shade them in to make sure that you are certain. Okay. Question 12. Also, question 12 is not a very long question. It's something that you either know immediately or you don't. When must an object be in equilibrium? There are 2 requirements for equilibrium. Not one, as we often believe, and this is probably where they're trying to catch you out a bit, but for equilibrium we require 2 things. The net force on the object must be equal to 0. But if the net force on an object is equal to 0, I'll do an example just to show you. If I have another plank, we'll use another plank as an example. If I apply a couple to this plank, a couple is a pair of forces with the same magnitude acting at the opposite ends. It's a nice uniform plank. What happens is the net force is 0. But is this object in equilibrium? No. There's a torque. There's even an angular acceleration. And so to prevent this from happening, so here we have that the net torque is not 0, even though the net force is 0. So this plank is not in equilibrium. So for equilibrium, we require net force to be 0, but we also require no torque on the object. The net torque should be 0. I just gave it the Greek letter tor because I'm too lazy to write the word torque out. It's just physics teacher things. And so this corresponds to option B. No resultant force, no resultant torque. And so again, I mean, immediately if you know what equilibrium means, then you can easily just pick out that answer. So the last few questions haven't been that long. It leads me to believe that they're setting us up for something more sinister. Question 13. A uniform diving board is held by 2 fixed rods at point P and Q. A person stands at an R if the diving board is shown. Now, the forces exerted by the rods on the board are vertical. The board remains in equilibrium as the person moves slowly towards Q from R. Which row describes the changes to the magnitudes of the forces exerted by the rods on the board? Okay, so we're looking for the sinister question. I think we've found it. I'm going to draw a diagram here. I think that this one requires some time and effort. It's one of those where you may have to just put a star next to the question and come back to it at a later point, depending on how confident you're feeling. So there's a rod P that's applying a downward force on the diving board. It's above the diving board, pushing down. There's a rod Q pushing up on the diving board. So we'll call the force at P FP, very original. The force at Q we'll call FQ. the weight, it's uniform, thankfully. So the weight of the diving board is through its center. We'll call it WR. And the weight of the person we'll call WP. And that acts at point R. And so there's a lot of things happening here. We'll call the central point O as well, just because we're running short of letters. And so the central point is O for origin. And let's start labeling some distances. I know this seems a bit tedious, but I want to be thorough. And if I decide by myself to label the distance from P to R as x1, remember the person's moving from R towards Q. So x1 is indeed a variable. And the distance from Q to R, I'm going to call it x2. Now what I want to know is how the magnitudes of the forces change as the person moves toward Q from R. So these values of x1 and x2 are going to change, and in response, Fp and Fq are going to change as well. And we want to know how Fp and Fq change as x2 gets smaller and x1 gets smaller. Okay, so what I'm going to do is first take moments about P. Moments are important here. Whenever you see a rod or a plank with masses on either side, then immediately you know that forces are important, but moments are as important. So I'm going to first take moments about P. If I do this and I start with anti-clockwise moments, I have PQ times the force FQ. PQ is the distance between P and Q, the horizontal distance, the distance that's perpendicular to the forces. And if I consider then the clockwise moments, I only have one anti-clockwise moment. It's only the force FQ that's going to cause the diving board to tilt anti-clockwise. But the weight of the diving board and the weight of the person are going to cause the diving board to rotate clockwise. And so the clockwise forces are PO times WR plus WP times X1. Actually, I should just put a multiplication sign to stick with the convention. So that's X1 times WP. So what I see from here is that as X1 decreases, we have to remember one thing here. WR is not changing, WP is not changing. PO is also not changing, PQ is not changing. So that's remaining constant, that's remaining constant, WP is remaining constant, FQ is going to change, but PQ is not going to change. And so if I adjust X1, if I decrease X1, what does this mean? FQ must decrease as well. I'm decreasing the right-hand side of the equation, and so too shall the left-hand side decrease. And so FQ decreases. Okay, that's good. I know that the force at Q decreases, so I eliminated options B and D. I'm left with A and C, but obviously I still have to figure out what's going to happen to the other force, Fp. So if I do a similar thing, and I take moments about Q, then what I get is, if I do the same thing, I find that anti-clockwise moments, PQ times FP is equal to QO times WR plus x2 times WP. Using the same logic, I see that as x2 decreases, then so too does FP. FP decreases as well. So by decreasing the distance x1, the distances x1 and x2, basically as the person walks toward the left, both FQ and FP decreases. Now, you could probably look at this logically and see this from the scenario, but at least if you have a mathematical backup, something to fall back to, then it becomes a little bit easier than trying to define and understand and create these images in your head. And so what this leaves us with is option A. And so the mathematical way works fine if you can't visualize it, because it also ensures that you do get the correct answer. So if you see a question like this, always revert to finding moments. Moments will be the thing that helps you in a question like that. Next one says the solid block has sides of length L, 2L, and 4L. It is submerged in water of uniform density, so the faces with the largest area are horizontal as shown. There's an upthrust acting on the block U. It is then rotated to a new position so that the faces with the smallest area are horizontal. The block remains fully submerged. What is the upthrust acting on the block in its new position? Okay, so we take the blocks in this configuration, we rotate it, and we stand it so that it is now standing on its smaller edge. And so again, if I draw this very poorly, which I'm currently doing, this is what it would look like. So the block is standing on its smaller edge. So it's the same block. We just place it on the smaller area, and we want to know that if we submerge it in water again, will the upthrust change, and if it does, what is the new upthrust? Well, I'm just simply going to remind myself what upthrust is. Upthrust is density times volume times G. Okay, so that the density of the object is not changing, the density of water is not changing, the volume of the object, the volume of water displaced, remains the same because the object is fully submerged. So the total volume of the object is still underwater. And G is a constant. And so the new upthrust is still rho v G. Nothing has changed. No densities have changed. The volume of the object and the volume of water displaced hasn't changed. And so the upthrust doesn't change. And so maybe a little bit of a trick question, but the answer there is B. So all I really needed to know was what the definition of upthrust is. How do we define upthrust? Rho v G. So just be careful with trying some mathematics. They try to catch you out with the 2's and 4's and some mathematics, but it doesn't change what the upthrust is, and the upthrust remains constant. Next, we have question 15, which is, in a large container in an oil refinery, 3 oils of different densities are mixed. No other chemical activity occurs, and we want to know the density of the final mixture. We have 1,200 kilograms of oil of density 1,100 kg per cubic meter, 1,500 kgs of oil of density 860 kg per cubic meter, and 4,000 kgs of oil of density 910 kg per cubic meter. What is density, first of all? Now, there's a temptation here to take the 3 densities and then find the average. And then the guaranteed that average will be one of the options here. I think if you calculate the average, you get 933. The temptation is just to take the average of densities. Obviously, the mixture will have the average density, but that's not the case. Remember, density is mass over volume. So you have the unfortunate task of finding the volume of each type of oil of each density of oil. Each type of oil has a different density. You have to find the volume for each type, which hence allows you to find the total volume. So what I will do is I'll give you a starting point. The mass of the first type of oil is 1,200 kgs, and its density, ρ1, is 1,100 kg per cubic meter. And so its volume, V1, is, so volume is mass over density, 1,200 divided by 1,100. And so I can just leave it as is. In simplified form, 12 over 11 cubic meters. Aha! I can now do the same for V2 and V3. And I get the volume of the second type of oil to be 75 by 43 cubic meters, just leaving my answer as a fraction. And V3 is 400 over 91 cubic meters. Why did I do this? I did this so that I can now find the total density of this mixture. The total density, I'll call it rho T, is the total mass, 1,200 plus 860, or rather 1,500, adding the masses here, plus 1,500 plus 4,000 divided by the total volume, which is 12 over 11 plus 75 over 43. It is messy, but it's required, plus 400 over 91. And guess what? This gives you a total density of 927 kg per cubic meter. So be careful of falling into the trap of finding the average of densities. Also be careful of falling into the trap of just finding the densities in their ratios. You're going to have to find the volume for each and then find the total density of the mixture, because that's the definition of density, total mass over total volume. That's question 15. That corresponds to option A. So a little bit of calculation required. It's a little bit of a long question. Question 16 shows a box sliding down a rough ramp. We're told that the change in gravitational potential energy of the box is 16 joules as it moves between positions X and Y. The box has 24 joules of kinetic energy at X and 35 joules of kinetic energy at Y. How much work is done against the frictional force? And so what we'd assume if there was no, what we'd expect if there was no friction is that the change in kinetic energy would be the change in gravitational potential energy, since there aren't any other forces at work here. Unfortunately, we have frictional force. So what I know is that the energy at the top, the mechanical energy, will be greater than the mechanical energy at the bottom, simply because work is done against friction. So energy is lost as friction does work. And so if I apply the work energy theorem, I get that the potential energy at the top, which is all gravitational potential energy, plus the kinetic energy at the top must equal the gravitational potential energy at the bottom plus the kinetic energy at the bottom plus another term, which is the work done due to friction. We'll call it W with a subscript F. And so what this means is that I can solve WF. So WF is simply, and I have to put in my values, the gravitational potential energy of the box is 16 joules, or the change in gravitational potential energy is 16 joules. So EP top minus EP bottom is 16 joules. The difference in kinetic energy is 24 minus 35 plus 24 minus 35. If I do the calculation, the work done against friction is 5 joules. So I've lost 5 joules of energy to most likely heat energy because of the work that is being done against friction. And so this corresponds to option A. So that wasn't particularly long. You could have done that again without physically having to put pen to paper. My suggestion would be, though, to put the pen to paper, since it just provides you with some sort of clarity that your answer is definitely correct. Okay, question 17 says the total energy supplied to an electric motor is E. Energy Q is wasted and the remaining energy does useful work. What is the efficiency of the motor? So, what do I know? I know that the useful work here in this case, so I have a total amount of energy that's given to a motor. Some of the energy is going to be lost as heat and sound, etc., and the other remaining energy does actual work, what the machine is meant to do. The useful work is the total energy supplied minus the wasted energy, E minus Q. And we know from experience that efficiency is the useful work, or the useful work output, or energy output, divided by the total energy input. And so what this means is this is E minus Q all over the total energy input, which is E, which we can write as 1 minus Q over E, which, if we look very carefully, corresponds to option C. And so our understanding of useful work and efficiency are both required here. Write down useful work as an expression containing the terms that are provided, and then take that expression and put it into the equation for efficiency. Useful energy output, useful work being done, divided by the total energy that goes in. That tells you how efficient a machine is, how efficient the energy is. Question 18 says, objects with different masses are placed on the horizontal surface of a table. The objects are then raised to different heights above the table. The gain in gravitational potential energy of each object is the same. Which graph best shows the variation of the height h with the objects above the table with their mass m? Okay, so we want to know which of these graphs. We have a sort of a hyperbola, we have a straight line graph that has a positive gradient, we have a straight line graph with a zero gradient, and then we have an exponentially increasing curve. Now, we don't really know an equation that relates h and m, but what we do know is that gravitational potential energy in its simplified form is mgh for objects that are close to the surface of the Earth, which in this case they are. The masses are placed on the surface of a table. So the height h above the surface of the table is equal to EP divided by mg. Now, the gain in gravitational potential energy of each object is the same. So they each gain the same amount of gravitational potential energy, but they are raised to different heights. So EP remains the same, which means we can change this equation into a proportionality. EP is constant, and we know G is constant. That means the H must be inversely proportional to the mass. Okay, remember this is because the gravitational potential energy we said was constant. This makes it easy to identify what the relationship is. That means if I were to draw a graph of H against M, I would get a hyperbola. And so this corresponds to option A. So you see the information that the potential energy is constant helps us find the relationship between the height above the table through which the object is moved and their mass, which normally wouldn't be related in this way. So, question 19. 19 is a little bit complicated. We're told that two wires, P and Q, are made from the same metal and hang vertically from a steel girder. Wire Q has half the length and twice the diameter of wire P. Identical masses are then attached to the bottom of each wire, and both wires obey Hooke's law as they are stretched by the weight of the masses. We want to find the ratio of the extension of wire P over the extension of wire Q. Okay, so a little bit of a complicated problem. And so if we consider the wires, we are told that they are circular and they undergo an extension when we hang a mass at the bottom of each wire. And so we'll call the force that's being used to extend the wires F. We'll call the extension the length by which the wire extends E. The surface area of the wire we'll call A, and the radius we'll call R. So the radius of each wire is R, and the equilibrium or unextended length we'll call L0. And we know that the area, surface area, is pi r squared, which is pi d squared over 4, where d is the diameter. I'm just writing all this down to coincide with what we're given. Okay, so we have two of these wires. They're made from the same metal, hang vertically from a steel girder, so they're both at the same point. Q has half the length, but twice the diameter of P. The masses that are attached to the bottom of each are the same, and both obey Hooke's law. And we want to know the ratio of the extension of P to the extension of Q. So one's going to extend more than the other. So what I know is that the extension of P, extension in general, rather, or rather the Young's modulus E is the force that's applied, F, times the equilibrium length L0 divided by the extension E times the area A. This is the Young's modulus. But what we know is that Young's modulus is the same for both wires, since they are both made from the same material. So this is made from the same metal. So EP and EQ are the same. So what else do we know? We also know that the masses that are attached to the bottom are the same, they have the same weight, and so the force that's causing them to extend must also be the same. FP and FQ are the same, so we just call them F. I'm going to let the equilibrium length of P be L0, just for mathematical purposes. And the equilibrium length of Q is half of that. We are told that Q is half the length of P. The surface area of P is 1 over 4 pi d squared, but the surface area of Q is 1 over 4 pi. Now remember that Q has twice the diameter of P. So it's 1 over pi times 1 over 4 pi, and now multiplied by 2d all squared. We have to double the diameter. Okay, and so what happens is this simplifies to pi d squared. And so now I'm left with some mathematics that I need to do. And so if I just erase this, what I can now do is I can equate the Young's moduli, and I get that F L naught over 1 over 4 times the extension of P times pi d squared is equal to the same force F multiplied by a half L naught, so I bring the half L out in front, over EQ times pi d squared. And if I do a little bit of rearranging here, I'm left with the ratio of the extension of P to Q, EP over EQ, is equal to 8. And so the extension of wire P is 8 times that of Q, 8 over 1, which corresponds to option A. So this one, seems to be a pattern with Hooke's law, does require a little bit of calculation, where we are told to tweak the diameters, tweak the lengths, tweak the areas, etc., and see how the extension changes. Or tweak the extensions between the two wires and then determine how the diameters are different, something like that. So it requires a little bit of manipulation and some time as well. That's one of the longer types of questions you can get. Okay, question 20 says, which statement about elastic and plastic deformation must be correct? I'm just going to quickly draw a graph that represents what Hooke's law tells us up until a point. If I look at the force applied to a solid object, the object, if it obeys Hooke's law up until a point. And so if I increase the extension, if I pull a spring apart by applying a greater and greater force, then the extension is directly proportional to the force. This is true for a rubber band. It's true for a spring, a regular spring. And the force is proportional to the extension. But there comes a point where we reach the elastic limit and the graph begins to taper out a bit. It's no longer a straight line. This is when plastic deformation occurs, where there is no proportionality between the extension and the force. That's plastic deformation. So what we can see is that elastic deformation is reversible and plastic deformation is not. So we can extend our spring up until the limit and the spring will go back to its original size. But if we exceed that limit, the deformation is not elastic and the spring or the rubber band will not go back to its original shape. And so elastic deformation is reversible, but plastic deformation is not reversible. So the correct answer there is option D. And so again, we didn't have to draw a diagram for this, but it was just additional information that might be useful. So that question wouldn't take, or shouldn't take at least, too much of your time. Question 21 shows us a graph that shows the variation with time of the displacement of a particle as a progressive wave passes. So we're now moving on into waves. What are the frequency and amplitude of the wave? Now I think this is fairly straightforward. I need the frequency and I need the amplitude. As I know, if I have time on the x-axis before I find the frequency, what should I do? I should find the period. The period is the time that we have between successive peaks or successive crests, or any two successive points in phase. It's the time that it takes for one cycle to occur. And this time is clearly 10, not just 10, but 10 nanoseconds. So the period of the wave is 10 nanoseconds. And so the frequency of this wave, f, is related to the period as it is 1 over the period. And so this is 1 over, but not 10. It's 10 times 10 to the minus 9. Remember, it's a nanosecond. Nano is 10 to the minus 9. And so what I get is 1 times 10 to the power 8 hertz, which is a little bit of manipulation, 100 megahertz. Remember, mega is a million, 10 to the power 6, and it's an uppercase M. And amplitude is a maximum displacement. Maximum displacement is from the equilibrium point to a crest or a trough. And so this amplitude is easy to read off. It's 5 millimeters. So if I label that capital A, the amplitude is 5 millimeters. And so 100 megahertz and 5 millimeters corresponds to option A. Again, this shouldn't take that much time. You wouldn't even need to do any annotations or drawing on the graph, but you can just for peace of mind and just to make sure that you are labeling the correct quantities in the correct positions on the graph. Question 22 takes up a lot of real estate. The graph shows the variation of the displacement of an air particle with time as a sound wave passes through. So we are given the formation of the sound wave, the displacement versus time at least. The intensity of the sound is then halved, but the frequency remains constant. And the four graphs are shown to the same scale as the graph above, and we want to know which graph shows the displacement of the air particle. Okay. And so what we need to do is to figure out our relationship between intensity and frequency and intensity and amplitude. Now, intensity and frequency should remain the same. So what I should have is the distance between peaks should remain constant, which is not the case there. So I can immediately eliminate A. It's not the case for B. I can eliminate B. But what I can see is that C and D both have identical frequencies that are identical to the original case. So I'm going to have to choose between C and D, because changing the intensity does not change the frequency. The frequency is told anyway to remain constant. So what do I have? Well, I know specifically that the intensity is proportional to the square of the amplitude. So that means the new intensity, I'm going to call it I prime, over the original intensity is equal to the new amplitude over the original amplitude all squared. And if I do a little bit of mathematics, I get the new amplitude to be the original amplitude times the square root of the new intensity divided by the original intensity. Now, why am I doing this? Because if I look at the information given, I'm told that the intensity is halved. And so the new amplitude is the original amplitude times the square root of a half, since that ratio is a half, since the new intensity is a half the old intensity. And the original amplitude, if I just go on blocks, since I don't really have values, the intensity is 4 units, 1, 2, 3, 4 units. And so that's 4 times the square root of half. So the new amplitude must be 2.8 in units. And so what I need is 2.8 blocks, or just under 3 blocks. C is 2 blocks in height, and so the amplitude is not correct. But D has 1, 2, and just under 3 blocks, 2.8, which is the new amplitude, which makes sense and that agrees. And so the correct graph for displacement versus time is option D. A little bit of manipulation of the understanding of the relationship between intensity and amplitude. Okay, question 23 says, which statement is correct? Gases cannot transmit longitudinal waves. Longitudinal waves cannot form stationary waves. Solids can transmit both transverse and longitudinal waves, and transverse waves cannot pass through a vacuum. Well, actually, if you read this, we should be able to immediately see. I mean, sound waves can pass through gases. Sound waves are longitudinal waves. Sound passes through air, which is a gas, and so that one's immediately incorrect. Longitudinal waves cannot form stationary waves. Well, sound can produce stationary waves, also incorrect. Solids can transmit both transverse and longitudinal waves. This is not correct. Sound waves cannot transmit both transverse and longitudinal waves. They can happily transmit transverse waves. And if we were to just look at it at first glance, we can tell that that D is definitely true, because it says transverse waves cannot pass through a vacuum. Actually, made an error. The first two are incorrect. The fourth one is also incorrect because it says transverse waves cannot pass through a vacuum. But that's not true, because electromagnetic waves are transverse waves and they pass through a vacuum. And so what is correct is option C. Solids can transmit both transverse and longitudinal waves. So my apologies, but the correct answer there is C. So by the process of elimination, we've shown if we didn't know that C is correct. So we've eliminated A, B, and D as the incorrect answers, and we're left with option C. So indeed, solids can transmit both transverse and longitudinal waves. But the other options are all false, and so we're left with one that's correct. Question 24 takes us to the Doppler effect. We are told that a car is traveling at constant velocity directly towards a man standing in the middle of the road. The driver sounds the car's horn as a warning, and the horn emits a sound of a wave of constant frequency. A sound wave of constant frequency, rather. The frequency of the sound heard by the man is different from the frequency of the sound emitted by the horn. We want to know which of the statements is correct. Okay, so we know the Doppler effect is occurring, but we are told that the frequency of the sound emitted by the horn is greater than the frequency of the sound heard by the man. The frequency of the sound heard by the man depends on the distance between the car and the man, and the sound waves continually accelerate as they move from the horn to the man. The wavelength of the sound heard by the man is less than the wavelength of the sound emitted by the horn. Okay, so the car in this case is driving towards the man. So I'm going to again showcase my artistic skills, or lack of artistic skills. This is a car, believe it or not. It's moving, in this case, to the right with a speed Vs. It's a source, so we'll give it a subscript S. The frequency of the horn as heard by someone in the car is Fs. Now, as we know from the Doppler effect, the car is moving in the direction of the sound waves, and so the sound waves appear to be compressed, which means that the observed frequency is much higher because successive sound waves reach the observer in a shorter time interval, and the sound waves behind the car are more spread out, and that frequency appears to be slightly lower. And the speed of the sound waves is the speed of sound at A, we'll call it v. Now the frequency observed by the person in the middle of the road, since the car is traveling toward them, Fo, must be larger than Fs. And if we go to our data sheet, we know that for the Doppler effect, the observed frequency is the frequency of the source times the speed of sound in A divided by v. Now it's going to be plus or minus, but we use a minus to ensure that the denominator is very small. The denominator is small, the fraction is large, which means that Fo is indeed greater than Fs, which is what we want. We want the observed frequency to be higher, and that's why we have a minus sign in the denominator. Now, we know that the frequency is inversely proportional to the wavelength. Okay, so the frequency must go up. And so if the frequency is going up, which it does as the car is approaching the man, and the frequency is inversely proportional to the wavelength must come down. And so the wavelength of the sound heard by the man is less than the wavelength of the sound emitted by the horn. So the frequency of the sound that he hears is higher, but the wavelength is lower. So the wavelength of the sound wave as heard of by the observer is less than by the person in the vehicle, or by the sound that is emitted by the car. And so this corresponds to option D. Again, a long drawn out explanation is not required, a diagram is not even required, but if the scenario calls for it, at least you understand it. If you understand the Doppler effect, you can do this to convince yourself in a way. Question 25, moving on to electromagnetic waves now. You want to know which statement about electromagnetic waves is correct. A wave of wavelength 5 times 10 to the minus 6 meters is invisible to the human eye. They can all travel at different speeds in free space. They cannot be polarized. They consist of vibrating atoms. Well, what we know is that the wavelength of observable light is between 400 and 700 nanometers. And so maybe I'll just write this down. So the wavelength of observable light, so lambda for visible light is between 400 nanometers and 700 nanometers, with blue light being 400 nanometers in wavelength, blue-violet end of the spectrum, and 700 nanometer end is your red and infrared range. So what we can see immediately is that 5 times 10 to the power 6, if we were to use nanometers, is 5,000 nanometers. That is well outside our range. And so immediately we can see, unfortunately, we have to know the wavelengths of the different parts of the spectrum. And so we can see that A is the correct one. That wavelength is indeed invisible to the human eye since it falls outside the range of wavelengths for visible light. Okay, question 26 says that a stationary wave is set up on a string that is stretched between two fixed points 48 centimeters apart. At one instant, the appearance of the string is as shown. What is the wavelength of the stationary wave? So recall what a stationary wave is. So a stationary wave occurs when, in this case, we have a wave on a string. It's moving between the two fixed points. So the wave propagates, it reaches the second fixed point, it is then shifted by 180 degrees, so its phase changes by 180 degrees, as it is reflected and then moves in the opposite direction. And so just assume all of these are the same size. They clearly don't look that way, but we can just make that assumption. And what we know is that the length of the string, or rather the distance between the fixed points, is 48 centimeters. That means the distance between successive nodes here is 16 centimeters. Again, you have to understand what standing waves are, how they are formed, the difference between nodes and antinodes. And so that's 16 times 3 is 48 centimeters. And so a wavelength is basically the distance between 3 successive nodes, if I want to think of it in that way. Or if I think of my original understanding of a wave, one wave cycle will be that distance. So that's my wavelength, and that's 16 plus 16, which is 32 centimeters. And that corresponds to option B. So understanding of stationary waves, which is a complicated topic, is extremely important. Now, question 27 tests my understanding of stationary waves in greater depth. We have a pipe that is closed at one end with a loudspeaker at the open end, and for some frequencies of sound from the loudspeaker, a stationary sound wave is formed in the air within the pipe with an antinode at the open end of the pipe, which we should know anyway. The length of the pipe is 0.85 meters, and the speed of sound in air is 340 meters per second. We want to know which frequency of sound from the loudspeaker will not produce a stationary wave. Okay, so let's draw a diagram of what's happening. So here is my pipe. I'm going to assume that this pipe has a length L. Now, some frequencies, so the loudspeaker's dialing through frequencies, some frequencies are going to generate a standing wave and other frequencies are not. And I want to know which frequencies will generate a standing wave. So remember, I have a standing wave when an antinode is formed at the open end. So I could have the simplest case occurring where there's an antinode at the open end. And remember, at the closed end of a pipe, no vibration can occur. Sound cannot form and there's no amplitude, there's no vibration of the air molecules at that point. And so there always will exist a node at the closed end. So an antinode must exist at the open end, and a node must exist at the closed end. And so I need to draw diagrams of standing waves that always have an antinode at the open end and a node at the closed end. So I can also draw a different one that has an antinode and then a node and then another antinode and then a node at the closed end. And just like before, a sound wave or a standing wave is one that's reflected. And so an antinode, a node, and there must be an antinode at the open end. So these are the different frequencies, the different types of standing waves that are going to be produced. Now, how do I know what frequencies are going to generate these patterns? And I can draw other patterns as well, as long as I have an antinode at the left-hand end and a node at the right-hand end. So what I can see is that L is equal to, now if I look at the graph that I drew first, or I look at the wave that I drew first rather, the standing wave has a wavelength, or at least the length of the pipe is a quarter of a wavelength. Because if I were to continue this forward, I've only drawn a quarter of a wave. It's poorly done, but the black graph or the black wave is only a quarter of a wave. And so it's lambda over 4. But it's also, if I look at the red wave, 3 lambda over 4. the red wave is 3/4 of a wave. I've drawn half a wave, a quarter of a wave, and I'm missing the other quarter. So I've only drawn 3/4 of the full wavelength. And so what I can see is a pattern's emerging. It's lambda over 4, 3 lambda over 4, 5 lambda over 4, etc. And that's 2n minus 1 times lambda over 4 for any integer values of n. And so I can continue, and this would be the pattern. And so what this means is the wavelength, lambda, if I just rearrange these equations, is 4L or 4/3 L or 4/5 L, and you can see the pattern. Now, frequency is speed over wavelength, because the wave equation tells us that v is f lambda. So frequency is v over 4L, 3v over 4L, 5v over 4L, and so on. So the frequencies that are going to generate standing waves are these. And guess what? I know the speeds of the waves, always 340 meters per second, the speed of sound in air, divided by 4 times the length, which again is always constant, 0.85, and then 3 times 340 meters per second divided by 4 times 0.85, and then another one would be 5 times 340 times 4, or divided by 4 times 0.85. And guess what? This is 100, and obviously 3 times 100, which is 300, 5 times 100, which is 500. And these are all in hertz. And so this corresponds, and we can see one is clearly missing here, and that's 200 hertz. So 200 hertz is the one that's not going to produce a standing wave. And so we can see that the pattern tells us that the answer is option B. Again, you don't need all the mathematics, but it is actually crucial to the understanding of what's happening. So we have to understand what standing waves are, how they're formed, and how we can determine their wavelengths and their frequencies from the type of pipe that we're using and the length of the pipe that we're using as well. Okay. Question 28 says water waves of wavelength lambda incident normally on an obstacle with a narrow gap. The width of the gap is equal to lambda, and the waves from the gap emerge over an angle theta as shown. The gap is slowly widened, which changes, if any, occur to theta and to the wavelength of the emerging waves. Okay, so we take the gap that we have and we slowly widen the gap. And we leave the wavelength of the waves. Actually, we're not too sure what happens to the wavelength of the waves. We're asked to determine that, and we also want to know what happens to theta. So if I widen this gap, I'm just going to draw on this diagram. If I widen this gap, so here's the incoming waves. They still have wavelength lambda. We want to know what happens to the wavelength after they pass through the gap. But now the gap is wider than they were before. So just going to, okay, let's assume that those waves are, the gap is much wider than it is before. What happens is there's just still diffraction that occurs, but the diffraction occurs to a lesser extent. So the diffraction occurs and the waves bend out less than they were before. And you can see that my dotted lines have a smaller angle between them than they did initially. And what this means is, although diffraction still occurs, diffraction occurs less, and so theta decreases. What we know is that d is inversely proportional to theta. The size of the gap, or the width of the gap, d, is inversely proportional to theta. So more diffraction occurs when the gap is smaller, and less diffraction occurs when the gap is wider. And so that means if I increase the width of the gap, then I decrease the angle theta. So that's going to correspond to, well, only option A. So I could immediately go to option A, but let's make sure that this stands firm. Does the wavelength remain the same? Well, is the speed of the wave changing? It isn't. It's still traveling at the same speed. The frequency is remaining constant. So the speed is remaining constant. The frequency is remaining constant. And so too is the wavelength. And so the wavelength also remains constant. And so theta does decrease and the wavelength does remain the same. And so the correct option there is option A. So yes, there's a big diagram and it can seem overwhelming, but in essence, it wasn't something that took a long time to answer. It wasn't a question that required a lot of time to answer. So we're still on waves, and you can see how important waves are. And that's why waves and superposition are such long topics, because they're significantly important and count a fair amount of marks. Question 29 says, light of a single frequency passes through two narrow slits and produces an interference pattern on a screen some distance away. The interference fringes are very close together. Which change would increase the distance between the fringes? Okay, so if I wanted the distance between successive fringes to change, what would I need to do? Okay, so I know that lambda is equal to ax over d, where in this case, A is the separation between the slits. Again, this is a double slit experiment, Young's double slit experiment. X is the separation between the fringes, which is what we're interested in, and D is the distance between the slits and the screen. And so this is for the double slit experiment. So I want to increase the distance between the fringes. I want to increase the distance x. I want x to increase. And so if I rearrange, I get x is equal to lambda d over a. Remember, the wavelength of light is constant, that is incident onto the slits. And so what I can do if I want to increase x is either increase d or decrease a. I can increase the separation between the slits and the screen, or I can decrease the separation between the two slits themselves. But clearly, there's only one option that's available here. And so if I want x to increase, I must have that the distance between the slits and the screen must increase as well. And that corresponds to option B. Increase the distance between the slits and the screen. Moving on to question 30, we are told that light of wavelength 5.4 times 10 to the minus 7 meters is incident normally in a diffraction grating. The separation between adjacent lines in the grating is 2 times 10 to the minus 6 meters, and the light that emerges from the grating falls on a semicircular screen as shown in the view from above. The grating is at the center of the semicircle and the lines of the grating are vertical. We want to know how many bright dots are formed on the screen. Okay, so a diffraction grating, we have light coming in, and the light comes in along a central axis. We assume that light behaves as a wave here, since it's going to undergo diffraction. We have a semicircular screen which is too terrible that I have to draw it again. Slightly better semicircle. And what we get is, since the light is diffracting from the grating, it's going to diffract out and it's going to form a diffraction pattern of bright spots and dark spots. And the central point will be bright. And then there'll be an equal number of bright spots on either side because of symmetry. So we aren't restricting any spots on either side, so we can have one bright spot at the center and then the others around it. And we want to know how many bright spots are possible. So basically what we want is, how do we find this number? We need to find n. We need to find the number of spots that are going to be visible as long as the diffraction can occur. And so we need to find n, the order of the diffraction when theta is equal to 90 degrees. Because if the angle is greater than 90 degrees, then the light will not form an image on the screen. It's going to be diffracted backwards. And so it has to be 90 degrees or less in order for the bright spot to be formed on the screen. And so we want to find n, and we know n, the order is d sine theta over lambda. And we are given d. D is the distance between adjacent slits, the distance between adjacent lines in the grating. And so sine theta is simply 1 because theta is 90. Sine of 90 degrees is simply 1. So this is d over lambda, which is the distance between adjacent lines in the grating, 2 times 10 to the minus 6 meters. Remember, this will always be a tiny number, divided by the wavelength, 5.4 times 10 to the minus 7 meters. And so what we get is 3.7. And so in this case, we're not going to round up because you're not going to get 0.7 of a dot. We can assume that you're only going to get 3. And so what we need to do is also consider the dot at the center. And so 2n plus 1, 2n plus 1, since they're, remember, this order of magnitude, or this order, is only going to be for the dots on one side of the grating. And so we have to multiply it by 2 to get the dots on the other side of the grating and add the 1 for the center. And so 2n plus 1 is 7, and that corresponds with option D. Now, question 31. The question 31 requires a little bit of calculation and an understanding of electrons and charge density. And we are told that a straight copper wire of diameter 0.42 times 10 to the minus 3 meters has a number density of free electrons 8.5 times 10 to the power 28 cubic meters. And in a given time interval, a charge of 0.15 coulombs moves through the wire. We want to find the average displacement of the free electrons along the wire in this time interval. Now, we do not know an equation that's going to tell us the average displacement of charge. We know how to calculate current and so on, but average displacement, not so much. Even drift velocity we know, but we're going to have to be a little bit manipulative in order to get the solution to this. So in order to save space, I'm just going to say goodbye to question 30. So question 31 requires us to put some knowledge of different pieces of information together. What I do know is that current, and I'm clearly going to need an equation that has number density. I don't know too many equations that has the the quantity number density in it, but I do know one. The current in a wire, I, is A times the number density, A being the surface area, the cross-section of the wire, and the number density of charge carriers, in this case electrons in the wire, V, the drift velocity of charge in the wire, and E is the charge of each of those charge carriers. What I also know is that current is the amount of charge passing a point in a given time, Q divided by T. And so this is equal to ANVE. Now a little bit more manipulation tells me that if I remember from my initial definition of velocity when I studied kinematics, is that velocity is displacement over time. So I'm going to write velocity as displacement x, which we want to calculate, divided by t. And so what I get is an expression that simplifies x is q divided by a n e. Now I suppose you could do this with some dimensional analysis, but it's easier, it's actually better to do it with the equation. And so the displacement, the average displacement of a charge x is the total charge, 0.15 coulombs, divided by, now this is the cross-section of the wire, which we can use the diameter of the wire, of the face of the wire, to find. That's pi times r squared. R is half the diameter, 0.21 times 10 to the minus 3, since that given is 10 to the minus 3 meters. We square that, multiplied by the number density, which is always going to be a very large number, 8.5 times 10 to the power 28. That's already in cubic meters, so that's fine. And then multiplied by the charge of an electron, 1.6 times 10 to the minus 19 coulombs. And what I get is the average displacement of free electrons in the wire in this time interval is 8 times 10 to the minus 5 meters. So quite a significant amount of charge moves through the wire, but the electrons don't do a lot of moving. And so this question could possibly try to catch you out, but if you understand the basics, you can do a little bit of manipulation and you end up with option C. So that's question 31. Question 32. Question 32 says, what is the definition of the potential difference across a component? Well, I'm just going to go to my definition of potential difference. The potential difference, by definition, is the work done per unit charge in moving that charge across the component. So the potential difference across any 2 points in a wire is the work done on every charge to move the charge between those 2 points. And so my options, I can look immediately and tell that the definition is energy transferred per unit charge. So immediately I can see that my answer is option B. And so I don't really need to spend too much of time on that because I already know the definition. So a good thing about defining or definition questions, at least in paper 1, is that it should be more direct and easier to get an answer. Okay, question 33 shows the IV characteristic for a semiconductor diode. Okay, so as the voltage increases, you can see an increase in current. And so we want to know what can be deduced from the graph. This is a little bit more application. Above a certain positive potential difference, the diode obeys Ohm's law. Okay. And this clearly isn't the case. There doesn't seem to be a relationship between the current and the potential difference. At least it's not immediately obvious from this graph. So we can't tell that I and V are related. Current is directly proportional to potential difference when the current in the diode is in one direction. Again, the current may be in one direction, as it is when V is positive, because current is constantly positive, but the graph curves. The graph isn't a straight line. There isn't a direct proportionality between I and V, like we said. And so that's definitely not what we can deduce from the graph. Option C says the diode has zero resistance when the current in the diode is in one direction. And there's no way that the diode will have zero resistance, but we definitely can't determine that from this graph. Diode having zero resistance, if we used Ohm's law, even if Ohm's law was applicable, would tell us, no, that's not true. There isn't a zero resistance for the diode. But what we can tell is the resistance of the diode depends on the potential difference across it. Okay, so the resistance, or the current at least, changes as the voltage increases. That's kind of obvious. The potential difference across the diode does determine the resistance of the diode. And that's basically what diodes do. So that's option D. There's a relationship between I and V. And if I changes, that means resistance is changing. So as the potential difference changes, the resistance of the diode changes as well. How do we know that? Because current is changing. So that's option D. Okay, we're getting near the end. We're onto the electricity part of the paper now. Question 34 says that a wire has a resistance of 30 ohms. The second wire is made from the same material, has the same mass, and is 3 times as long as the first wire. What is the resistance of the second wire? And so, fortunately or unfortunately, this one requires also a little bit of calculation. So if two wires are made from the same material, they have the same resistivity. That's a fact that will not change. As long as they are made from the same material, the same metal, they will have the same resistivity. So we also know that the two wires have the same mass. I'm going to write down what I know in mathematical form because this helps us later on. The second wire has a length L2, which is 3 times greater than the length of the first wire, 3L1. So what I want to do is I want to compare. So what I know is the densities. I'm told that the density is same material, 3 times as long. So I'm going to have to do a little bit of manipulation. I want to find the area because I know that the resistance is related to the resistivity rho, the length L, and the area A. So R for wire 1 is rho 1 L1 over A1, and R2 is rho 2 L2 over A2. But I don't know how the area is going to change. But what I can do is compare the densities. Since they are made from the same material, they have the same densities. So density being mass over volume, it's mass times pi R1 squared times the length. We're assuming that the wires are cylindrical and they have the same densities, and their volumes are pi r squared times the length. And this must equal to m2 over, now the length of L2 is 3 times L1, so that's 3 pi r squared L1. And so now I can do a little bit of cancelling. I know M1 and M2 are the same. L1 is common. This is R2 squared. So the radii are not the same. They can't disappear, but the pi's can. And what we end up with is, actually, we'll leave the pi's for now, because what we end up with is pi r2 squared over pi r1 squared is 1/3. Aha, so what this means is the area A1 is 3 times the area A2. Why is that important? It's important because if I go back to the equation that I had, so I'm just going to move everything so I can do a calculation side by side. So now I have R2 is equal to rho 2 L2 over A2. But now I can actually compare the resistances. So I want to know the resistance of the second wire, and I can tell the resistance of the wires now because I can compare the areas as well. So I know all things about the two wires. So R2 is rho 1, the same resistivity, times 3L1, and A2 is 1/3 A1. So what I get is 9 rho 1 L1 over A1, but hey, look, rho 1 L1 over A1 is R1. That's 9 times the resistance of the first wire, which is 9 times 30, which is 270 ohms. And that corresponds to option D. So here there was quite a significant amount of manipulation that had to be done. I had to figure out the areas, or rather compare the densities to figure out the areas. Once I've compared the densities, figured out the areas, I can then go back to my equation that had resistivity in it in order to find the resistance. So there was a significant amount of mathematics in there. Okay, question 35 also has a fair amount of mathematics in it. And so, since we are out of space here, I will just remove that working. Again, if you feel like you need to go back and understand and absorb it, please, by all means, pause the video at this point and make sure you are happy with what I'm saying and not just writing it down. It does take time to practice, do it for yourself, understand what I'm doing. So question 35 says we have a cell of resistance of internal resistance little r and EMF uppercase E. The cell is connected in series with an ammeter and a variable resistor of resistance uppercase R. Uppercase R is 10 ohms and the ammeter reads 0.3 amperes. Then R is 5 ohms and the ammeter reads 0.4 amperes. We want to find the value of E. So we have a variable resistor, we adjust the variable resistor, and we get different readings on the ammeter for different resistance readings. And we want to find the EMF of the cell. Okay, we're doing it experimentally here. We aren't given the option of just opening the circuit and finding and reading the EMF. So using the ammeter and some clever methods, how are we going to figure this out? So we know the EMF is the current in the circuit into the total resistance from Ohm's law. The total resistance of the circuit, since the internal resistance is in series with the variable resistor, is big R plus little r. So let's input the two scenarios that we have. The EMF remains constant. It does not change, irrespective if we adjust the variable resistor or not. And so E is the current 0.3 times the reading on the variable resistor 10 ohms plus the internal resistance, which also doesn't change. We call this equation 1. In the second scenario, E is 0.4 into 5 plus little r. We'll call this equation 2. We have two equations with two unknowns, and we can then solve simultaneously. If we solve simultaneously, we get E is equal to 6 volts. I mean, not difficult. What we can do is we can go to equation 1, simplify for r, or rearrange, solve for r, take that simplification, put it into equation 2, and then we have one equation with one unknown, which is E, and we find E is 6 volts, which is option D. So actually not too bad of a question. We just needed to remember that EMF is I times R, but the total resistance, since the eternal resistance and the variable resistor are in series, is R plus R. Okay, question 36 tells us that the sum of currents entering a junction in an electrical circuit is always equal to the sum of the currents leaving the junction. We want to know why this is. Well, there's a very specific reason, and this is actually a law. Not just any law, but can never get the spelling right. Kirchhoff's first law. I'm not going to go into detail with this, but basically you know the Kirchhoff's first law is simply a statement that comes from the conservation of charge. It is the conservation of charge in words. Or it's a consequence of the conservation of charge, rather. And this is option A. The sum of currents entering a junction in an electrical circuit is always equal to the sum of currents leaving the junction. That's Kirchhoff's first law, which is a consequence of the conservation of charge. So charge must be conserved when entering a node or leaving a node. Charge doesn't disappear at any point in a circuit. Okay, question 37 tests our knowledge of light-dependent resistors, or LDRs. An LDR has the circuit symbol of what is a usual resistor, but two arrows pointing towards the resistor at an angle. So we call this a light-dependent resistor. Its resistance changes when the light intensity changes. Now, in the circuits shown, the temperature remains constant. In which circuit does the potential difference V increase with increasing light intensity? Now we're also given thermistors. So a line that sort of changes direction like this, that is the symbol for a thermistor. Now the light intensity increases on all of these circuits, but in only one of them, the potential difference V, which is the potential difference across the resistor at the top, increases, and we want to know in which circuit this occurs. Now, the one thing we know is that as intensity increases, the resistance decreases for an LDR, or light-dependent resistor, and the current remains the same. Why does the current remain the same? Because these two are in series. So even though the resistance is changing between the two resistors because the light is affecting the LDR, there's nowhere for the current to go. There isn't a branch for the current to escape to. And so the current still has to pass through the two resistors, and so the current remains the same. So the intensity increases, R decreases, but I remains the same. And so the potential difference across an LDR will decrease. Okay. Okay, so the potential difference across an LDR will decrease, which means an LDR cannot be the source of V. So V cannot be across an LDR. So that immediately eliminates the options of C and B. But we need the voltmeter to be across the thermistor. Okay, and for the voltmeter to be across the thermistor, we need, and obviously there must be some change to the circuit. In A, we have a voltmeter across a thermistor, great, but light intensity doesn't affect the other resistor. So the only option we are left with is the option in which the voltmeter is across the thermistor, and that's option D. So the light intensity increases, which decreases the voltage across the LDR and increases the voltage across the thermistor, and so V increases, which is option D. And so that's a little bit of understanding of how a thermistor and an LDR can be used together. So it's important to understand both and not try to learn them in isolation. Try to understand what happens with the application of both of those circuit components, an LDR and a thermistor. Because in that question, an understanding of one won't really help you. Okay, now we move on to particle physics, the last three questions. We are told that carbon-14 decays into nitrogen-14 by emitting a beta minus particle. We want to know which statement explains why the beta minus particles are emitted with a range of different kinetic energies. Okay, let's think of what happens in this process. So I have carbon-14 nucleus. It decays via beta emission. It forms nitrogen-14 7. It also forms a beta particle. You have to understand beta decay. It's a beta minus particle. So the atomic number is -1 in this case, since an electron is negatively charged. And don't forget that an electron antineutrino is also produced in this process. It doesn't have a mass number or atomic number, doesn't contain any protons or neutrons. And also, there's some energy that is produced in this process. Now, what happens is this energy is usually given in the form of kinetic energy, a little bit of heat as well, but it's given in the form of kinetic energy to the products of the decay. And so the decay products rebound. They move off. Now, obviously, the nitrogen is fairly heavy. It's not going to move as much as the beta particle or the neutrino. So the beta particle is given a significant amount of energy. But the energy is not equally distributed. And so sometimes the energy is distributed more to the neutrino than it is to the beta particle. And so for multiple decays, we can have multiple energies that are being given to each individual particle. And so what this means is the energy that is released in the decay process is shared between the nitrogen, the beta minus particle, and antineutrino, and it's impossible to determine exactly what energy the beta particle will be given. And so that's why we have beta particles with different kinetic energies. They all have the same masses, so the only thing that can be different between them are their velocities. And this is purely because the energy is shared and not given discretely to each of the particles. And so the beta particles can all have different energies. Some of them can be greater than others and obviously more harmful in the process. Okay, question 39 says a nucleus of radioactive element emits an alpha particle, then a beta particle, and then another beta particle. Which statement describes the final element that is produced? Is it a different element of a higher proton number than the original? It is a different element of a lower nucleon number than the original. It is an isotope of the original element. It is the same element as the original element, but with a different proton number. Okay, let's assume that this nuclide was called X. It had a mass number A and an atomic number or proton number Z. Or let's call A nucleon number. It then became a nucleus Y, and its new nucleon number is A prime, its new proton number is Z prime. And in the process, we are told that an alpha particle is formed. Remember, alpha particles are helium nuclei, 4-2. A beta particle, -1-0, beta minus particle, and another beta minus particle. And so what I need to figure out is what my Z prime is going to be and my A prime is going to be. Now I can see Z prime plus 2 -1 -1. I'm basically considering all the numbers at the bottom on the right-hand side must equal the number on the left-hand side. That's equal to Z. But 2 -1 -1 is 0. So I should have that the proton numbers remain the same. The proton number is conserved. Same proton number. So I should have same number of protons, which makes sense. The nucleon number, though, on the left-hand side, or the right-hand side rather, is A prime plus 4, and on the left-hand side is A. And so what I get is A prime is A minus 4. So I have a smaller mass number or nucleon number. So what I have is the same element but I have a different mass number. If I have the same element with a different number of nucleons but the same number of protons, then the neutron numbers are different. The number of neutrons are different. If the number of neutrons are different, then what I have is an isotope of that element. So I've kept the number of protons the same, but my nucleon number is changing. So in the nucleus, if I have the same number of protons, but I have a different number of neutrons, I now have an isotope of the original element. And the word isotope appears in option C. So I have the same element, but an isotope of that element. Okay, lastly, we have question 40, bringing us to the end of this paper. How many hadrons, baryons, and mesons are there in a nucleus of beryllium-9? So let's look at beryllium-9. So beryllium-9, 4 has 4 protons. Remember, the bottom number, Z, is the proton number. And the number at the top, be careful, is not the neutron number, it is the nucleon number. And so there's 4 protons and 5 neutrons. So what does that mean? That means there are 9. So we need to divide the particles into their classifications. Now, any particles that undergo or can feel the strong force or can experience the strong force we call hadrons. And so, how many particles can experience the strong force? All of them. There are 9 hadrons, 4 protons and 4 neutrons, all of which can feel the strong force. Which of these are composed of 3 quarks? Well, protons are composed of 3 quarks and neutrons are composed of 3 quarks. Any particle composed of 3 quarks are called baryons. And so all of the hadrons are baryons. Remember, baryons are a subset of the hadrons. hadrons can be divided into baryons and mesons. Now, if all 9 of these particles are baryons, obviously it means that none of them are mesons. What are mesons? Well, you know from your notes that mesons are made up of a quark and an anti-up quark and an anti-down quark. Okay, and so there are 3 sort of building blocks for a baryon, but 2 building blocks for a meson. But protons and neutrons both have 3 building blocks, and so they are baryons. So we have 9 hadrons, 9 of those are baryons, and 0 mesons. And though this corresponds to option C, 9, 9, and 0. And so the correct option is C. So that brings us to the end of the paper. Now notice that the questions follow the same order as the topics do in your course outline. And some of the questions are more in depth than others. So you will not take the same amount of time for each question. Some questions will take you longer, some will take you less. The only way you can prepare for a paper like this is to be constantly practicing. And so the time management becomes sort of an innate ability, something that you become second nature to you. And eventually you realize that you can feel okay taking longer on some questions, and you can breathe on questions that are shorter. So until next time, I'm Mr. K. We'll see you again on Everything is Relative for some more A-level physics.